We're going to be taking nth roots of complex numbers, really just rational numbers, but it's important to know how to do it for all complex numbers. In particular, sometimes we're going to take nth roots of negative numbers, and the n is even, so like square roots of negative numbers, fourth roots. And so it'll be helpful to know how to do that. So we're going to start, so what do I mean by this? I mean, given a and c, we want to solve the equation t to the n minus a is 0. And we're going to see that this has exactly n solutions. And the question is, what are they? Give me a formula. So that's what we're going to try and do. So we're going to start with the nth roots of 1. And 1 is often called unity, so the nth roots of unity. That is, we're going to find all solutions to t to the n minus 1 is 0. Or t to the n equals 1, or all the nth roots of 1. Okay, so to do that, we're going to introduce, I've never been able to do a zeta. I'm not going to draw a zeta well in this class. I'm sorry. But we're going to introduce zeta sub n. And zeta sub n is e to the 2 pi I over n. This is cosine 2 pi over n plus I sine 2 pi over n. Okay? And let's notice something about zeta n. Zeta n to the n is e to the 2 pi I over n to the n, which is e to the 2 pi I, which is cosine 2 pi plus I sine 2 pi. And sine 2 pi is 0, and cosine 2 pi is 1. So zeta sub n to the n is 1, so it's an nth root of 1. And in fact, all of the other powers are nth roots of 1 as well. So moreover, zeta sub n to the I to the n is zeta sub n to the n to the I is 1 to the I is 1. Let me not use I, because I is sacred. Let's use k. K, k, k. So all the powers of zeta, and all the powers of zeta, let's just say for in between 0 and n, the 0th power being 1, all the powers of zeta are going to be different complex numbers. In fact, we can graph these. So how do you visualize these guys? Let's do n equals 3 at the start. What we're going to do is we're going to draw the unit circle. We're going to mark 1. 1, of course, is a root of 1, because 1 to any power is 1. And then we're going to put 3 points total, but 2 other points on the circle equally spaced apart, so that this makes an angle of 2 pi thirds, this makes an angle of 2 pi thirds, and this one makes an angle of 2 pi thirds. This is e to the 2 pi I over 3, which I'm calling zeta 3. And this one is zeta 3 squared, which is e to the 4 pi I over 3. 4 pi I over 3, sorry. And that's how you visualize them. So how would we do n equals 4, for example? Well, we do the same thing. So we draw the unit circle. There it is. Mark 1. There it is. Put 3 other points equally spaced, making an angle of 2 pi over 4, which is pi halves, which is 90 degrees. And so we get zeta 4 is actually I. Zeta 4 squared is negative 1, and zeta 4 cubed is negative I. And since I computed these, let's also compute these. If you sit there and you work out the algebra, you get negative 1/2. So you work out the cosine of 2 pi over 3 and sine 2 pi over 3. You get negative 1/2 plus root 3 over 2i, and you get negative 1/2 minus root 3 over 2i. And that's what you get. N equals 5 is similar, and so on. Now, the case n equals 4 is interesting. Not all of the powers of zeta are kind of, there's some powers of zeta that they don't give you all the other powers if you were to take powers of them. That was convoluted. What am I trying to say here? I'm trying to say that this guy here, this zeta 4 squared, is interesting. It's interesting because if we were to look at n equals 2, that is looking at the square roots of 1, there's 2 square roots of 1, there's 1 and negative 1. So zeta 2 is negative 1. So zeta 4 squared was a previous zeta. It was zeta 2. So this gives us a definition. A primitive nth root of unity is an nth root of unity. So one of these powers of zeta, of the standard one, such that it is not an mth root of unity for any m less than n. So in this example up here, the primitive guys, the primitive fourth roots are here. They're plus or minus I. Zeta 4 squared, this one is not primitive. And if you know some group theory, if you look at the subgroup generated by the corresponding zeta, it's primitive if you get everything, and it's not primitive if you get a proper subgroup. If you don't know that, that's also fine. So the primitive ones are the ones that don't come from a primitive, from a root of unity for a smaller power. Those are the primitive ones. And a proposition for detecting them, these are detectable. Let's let zeta n be as before. The standard primitive nth root of unity is what we'll call it. Then zeta to the k, zeta sub n to the k, which is e to the 2 pi I k over n, you just raise it to the kth power, is primitive if and only if the GCD of k and n is 1. That is, k is relatively prime to n. And we saw up here in our example, zeta 4 squared, 2 and 4 are not relatively prime, so it was not primitive. 3 and 4 are relatively prime, and it was primitive. Okay, so this is just a generalization of what happened in that example. Let's do a quick proof, and then in the next video we'll tackle general nth roots. So let's see here. Let's suppose that zeta sub n to the k is not primitive. What does that mean? It means that zeta sub n to the k is an mth root of 1 for some m less than n. And that m is going to have to be a proper divisor of m. So some m that properly divides n. The only possible way such a power could be 1 is if it's a proper divisor. That's something that you'll have to think about for a second. It has to be a divisor in particular, but if it's not primitive, it has to be a proper divisor. So that's just a consequence of the expression e to the 2 pi I over n. Anyways, suppose not primitive, then this is true for some m that properly divides n. Then what? Well, n is equal to mr for some, again, these m and r are less than n. It's a proper divisor. But r is bigger than 1. All right. Then what? Well, zeta, oops, sub n to the km, well, that's 1. And if we were to write out what zeta sub n to the km is, this is e to the 2 pi I km over n is 1. So e to the 2 pi I over n is zeta n, and we raise that to the km power. But this is cosine 2 pi km over n plus I sine 2 pi km over n. And the only way this is equal to 1 is if km over n is an integer. And so in particular, because that will make the cosine part 1, and that will make the sine part 0. In particular, this means that n divides km. But n is equal to mr, so mr divides mk implies r divides k. Since r divides n, because n is mr, we get, we have that r is a divisor of k and n. And so the GCD is at least r. It might be bigger than r, but it's at least r. And r is a proper divisor of n, so it's m was a proper divisor of n, so r is strictly bigger than 1. So the GCD of k and n is bigger than 1, so they're not relatively prime. Okay, so let's see. We saw that if not primitive, then the GCD is not 1. And now we're going to suppose the GCD is not 1 and show not primitive. So we're doing contrapositive in both directions. So if the GCD of k and n is equal to some r bigger than 1, then, well, what do we get from this? We know that r is a divisor of k, and r is also a divisor of m, and we're going to choose to write that as n is mr for some, again, m in between 1 and n. Then from this, we get that k times m is, again, divisible by m times r, because r divides k, so mr divides mk, but mr is equal to n. So zeta sub n to the k to the m is equal to 1, but m is less than n. So we found that zeta sub n to the k is a root of unity for a root that has, how do I say this? A root of unity for mth root of unity for m less than n. Okay, so zeta sub n to the k is not primitive. Okay, so this was a little convoluted, sorry. But nevertheless, there's a way to check which ones are primitive. It's the powers that are relatively prime to, well, the powers of the standard primitive one that are relatively prime to the whatever n you're looking at in the case.